necessarily wanted to spend. I'm looking forward to getting my head back. So next lecture we will be back to our normal setup. All right, sets. So we talked about lists, and lists were the first container class that we learned. Okay, and the property of lists are you can put anything into a list, right? So you can put in, lists can contain multiple things, right? So we can come in here and we can do L equals range 10 L dot append Google L dot insert 0 comma 3.5 L dot insert list L dot insert L dot copy. Let's see what that does. Okay, so we can have a list, and the thing to remember, range has no sorry, missed the list. 2 years ago this would have worked. Oh, all right. That part wouldn't have worked 2 years ago. And now we can look at L, and what we see is we have the 3.5, and then we have 3.5. This would be our list at the point we put in this line 11. So basically, it's a mixture of things, but there's an order to it, and it will always come out in the same order, right? And L sub 0, well, it's whatever we put in the 0 range. L sub 1 should be the list, the previous version of the list. L sub length L minus 1 should be Google. L sub minus 1 should be Google, right? So it's a list. It's ordered. It has a specific order. That specific order is always the same. We can have multiple copies of something in a list. We can say L dot append Google. And we can spell append incorrectly once just to demonstrate that you have to be able to type. And then we can do it correctly. And we can find out that we actually have 2 Googles in there, right? So lists allow you to have ordered entries. They allow you to have any type of data in there, and they allow you to have duplicates. What we want to talk about now is we want to talk about, and that's a container class. What we want to talk about now is we want to talk about a different container class, and the mathematical abstraction of this data class is a set. So when you have a set, what you have is where do I talk about this? Okay. That's this paragraph here, by the way. When you have a set, you have something that is unordered. So you can look at the elements in a set, you can pull them out one at a time, but there's no set specific order for them. You need to be able to handle things that come in and out in different or come out in a different order than you put them in. So sets are unordered. Sets can hold most things. They can't hold all things. In particular, if we want to look at the definition of what they can hold anything that's hashable, and we'll talk about that a little bit, in a bit. But basically, they can hold anything that maps into a hash tag or a hash, not a hashtag. They're unordered. They can hold most things, and they can't hold duplicates. They will not allow you to add duplicate data. And those are the 3 important things about a set. So we're going to look at this in the context of finding all the people in an IMDb file. And if you go to Submiti again, right? And we come into the course materials, and you come into the lecture notes part, grab this file here, lecture15files.zip, and unzip that. That has some data in it that's going to be kind of useful to you. And in particular, what it has is it has forcing me to type in Windows. If we look at this, it's got 4 files: hanks.txt, imdb 2010 through 12.txt, imdb data.txt, and then this lecture15 find names start.py. That's this code here. We're gonna play with this a little bit to kind of show you what we're talking about. But if we look at, for example, the imdb data.txt file, what we're going to find out is that this is a huge file, well, relatively huge. It has 260,000 lines. It's an excerpt of data from the Imdb database, so that's a database of movies. And what it has is it has a star's name, or a person appearing in the film's name, or worked on the film. Then it has the name of the film, and then it has the year the film came out. So there's only 3 fields in this file. The 3 fields are separated by these vertical bars or pipe characters, and there's 260,000 of them. So we're going to run some different algorithms on this to kind of show you why we need sets and where sets excel and are powerful. You'll notice that this is, I believe, last name, comma, first name. So that'll kind of play in when we're talking in your lecture exercises. So the very first field is the actor or the participant in the film, and it's in terms last name, comma, first name. You will need to keep that in mind as we're moving forward. All right, so 260,000 of those. Let's look at this little code. I put in this import time was in. I put in this start time and this end time. And let's put in a little thing here to print out start, end minus start. And we're going to start off, it's going to be pretty fast. I think I'm introducing a new command here. The command I'm introducing is time, right? Time just tells you the number of seconds since some fixed time in the past. So if you do import time, with the correct syntax, and then you do help time with the correct syntax, what you'll find out is that the time command returns the current time. Returns the current time in seconds since the epoch. The epoch is just that fixed time in the past that time counts from. So I think it's January 1st, 1970 or something. It's long enough ago that we don't have to worry about hitting it in general. But it tells you, a given time, and then we can take and subtract it off. It does return, I believe, a floating point number, so we can actually run this, and let's see what we're doing. We're asking for the name of the IMDb file we want to look at. We're generating something called a name list, and then we read in the file. This encoding is important because the file contains foreign characters, accents from characters in different languages. So this just says, don't expect this to be American or UTF. I'm sorry, don't expect this to be ASCII. You have to handle characters other than just ASCII characters. You will need this in your code. There are alternate encodings in ISO 8859-1. We give you a couple of different ones in the labs, and I think in the exercises. In general, it doesn't matter what you use here as long as it's not ASCII. So we go through, we read a line, we take that line and we split it at the pipe character to break it up into the 3 fields of person's name, movie name, year it was released. And then what we're just going to do for right now is you're just going to pick out that first word, right? This gives us a list of the fields, and we're going to strip it out because when we look at that file, we have an awful lot of white space. And that's all we're going to do. So we're just going to read through this entire file and strip out the first name. And we do, right, I'll say imdb data.text. And it turns out we didn't actually do anything, but we did nothing in about 0.8 of a second. So we can handle that. We can do nothing in 0.8 of a second. Nothing's a good thing to do in 0.8 of a second. I do nothing in 0.8 of a second pretty much every day. All right, so now let's start looking at the actual problem we want to solve. If we go out to our setup here, right, this is an excerpt with a lot of the spaces missing. Let's say we want to find all the unique people in the file. So we want to count the number of different people that we run into. Or maybe we want to do something like ask if a specific person is named in the file. The problem is that if we look at this file, what we're going to find out is that some people appear a lot of times. So let's look for Hanks. Tom's in there a bunch. Hanks, comma, Tom. Right, there's 1 time, twice, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So he's there a bunch, and we're only 54% of the way through the file. We don't want to count him every time he's in there. That wouldn't give us an accurate count. So if we want to find out how many different people are in that file, we have to have some way of determining that Tom Hanks, we've already seen Tom Hanks, and we don't want to deal with him again. So let's go back to our handy dandy notebook, and you'll see that one of the things we set up here was we set up this name list. And we know that we can put people into a list. So as we see a new person, a person we haven't seen before, we can add them into our list. So we can come down here and we can say if name not in name list, right? Name list starts out as an empty list, and then as we come through here, we'll just say name list dot append name, and really that's all we have to do, right? So at this point, what we've done is every time we see a name, a new name, right? We check if they're not in the name list already, we put them in, and at the end we can say we'll still measure the time, but we can also say print we found different, and I'm going to call them people. I think some of these may be animals, but that's okay. People are animals too. And the number we found is just how many people we put into our name list, so it would just be the length of the name list, right? Okay, so this looks pretty easy, and I'm willing to believe this. But before we test it, let's think about this a little bit. IMDb data has 260,000 entries. How are we going to possibly know that our results are correct? Okay, I've given you some alternates, right? We have IMDb data 2010 through 12.txt. That's about 1/10 of the size. right? So if we look at that, right, that gives us, instead of 260,000, it gives us 25,000 lines. That's still quite a bit to test with. So maybe what we'll do is we'll just look at our smallest data set. And our smallest data set, the reason I looked at Tom Hanks, is hanks.txt. And it turns out that hanks.txt has 68 lines, and it has Jim, Colin, Bethan, Tom, Zach. I think there's 13 of them. And then Colin and Tom get intermixed there for a while. Did we get Jim? We have Jim, Bridget, Scott, Mark, Brad, Steve. I don't think we had Steve yet. Then there's Christopher, which is different than Chris, I think. And then there's Mike or Paul. Anyways, I think we have 13 of them here, if I counted correctly, as opposed to counting just randomly. So we can come back and we can say we can find, we can certainly count through this 68 lines and find out how many are there. So let's just start running our solution, and let's start off with something simpler. Instead of running on the big file, we're just going to run on the small file, right? So I'm going to, instead of IMDb data, I'll just end it in hanks.txt. And we were right. We found 13 different people, and well, it didn't take us very long. It took us even less time than going through all of the IMDb data things. I'm not really sure why that is. Probably there was just something else running on my machine. Probably the frame grabbing software that made this one artificially slow. But we got through this in 9/10 thousandths of a second. 9/10 thousandths of a second, or 99 hundred thousandths of a second, or something like that. So we got through very quickly. We found 13 different people. We can look at name list. We can see them. Name list, and this is in the order they were added: Jim, Colin, Bethan, Tom, Zach, Bridget, Scott, Mark, Brad, Steve, Christopher, Mike, and Paul. So that's pretty good, and I'm willing to bet. I'm willing to believe that. I think if we went back and counted through again, we would find 13 of them, because that's the number I had in my mind from counting it this morning. So that's all fine. And this is a problem with big data, is that when you want to start looking at big things, you have to figure out how to stress it, or how to test it without having to go through all of that big stuff and manually brute force a solution to the 260,000 records that we know about. Okay, so now we've kind of moved up. So now let's run it again. I'm going to step right to the big guy. We'll run it for IMDb data.txt. And this took, the first time we ran it, it took, 9/10 thousandths of a second. So I figure it's going to be a lot slower. Well, you know what? Let's run this on this second file first, just so that we can get some idea. We know that this IMDb 2010 to 12, that's actually about 1/10 of the size of the full file. So whatever we have here, there'll be 10 times more data in the other file. So let's just kind of run through this, and I'll talk for a few minutes while we go along. And this is not 9/10 thousandths of a second. Okay, 20,455 people. I have no idea if that's right. And it took us, well, a quarter of a minute, 14 seconds. Let's say 0.00099. Was that what we had the first time? Yep. 0.00099 times 2455 divided by 68. So what we're trying to figure out is how many times slower is this than, well, I don't know what I was trying to find out. Let's do 14.6 divided by 2455. To find a successful answer on this one, it took us 0.0007 seconds. For the other one, and I'm not really sure what this shows us. There were only 13 successfuls, right? So this is about 7 times 10 to the 4th. This is about 7 times 10 to the minus 5. So it's saying our per answer cost has gone up about 10 times. So that's kind of interesting. That's not per item visited. That's per successful answer. But that's something to think about. We also know that we had 25K entries. So per entry, 14.6 seconds. Divided by 25K, essentially. 0.006 seconds per entry in the list. If we look at the Tom Hanks data, that was 0.00099 divided by 68. So, yeah, again, this is significant, right? For each entry, for each of the 68 lines, it took us 1 times 10 to the minus 5th the first time. It took us essentially 6 times 10 to the minus 4th the second time. So there's something going on here. It's not just taking us proportional to the number of data items in the file. It's taking us substantially more than that. We'll run the big dude. Imdb data.txt. All right, and now I'm going to have to talk for a bit. In fact, I'm not sure at what point this is actually going to end. Depends on whether my system gets busy or not. It will be a little while, though. So let's start thinking about this. And what I want to look at in particular is I want to look at this if statement. So we have a list. And the list, we're asking this simple question: is this name currently in the name list? And if the answer is false, we put on another, we add another name to the list. If the answer is true, we just skip it, right? We don't put it, nothing changes, except we go on to the next line. And the interesting thing here is, well, the first time through the loop, there's nobody in the list. So this test is trivial. The second time through the loop, there's one person in the list. So it takes us a little bit longer. By the time you go through and have 25,000 people in the list, this line starts taking up some significant amount of time. And the bigger the data we have, the larger that line gets. So if, for example, the number of successful finds in the file is on the same order, right? If it's some fixed fraction of the number of lines in the file, what's going to happen is by the time you get through the end for those last few entries, you're going to have to search through the entirety of the list again. And this is slow. In fact, it's slow enough that maybe you guys don't even believe this is doing anything. Stop that for a second. Counter equals 0. If counter modulo 10,000, I'll do 1,000. Okay, so every 1,000 entries, we're actually going to print out our counter variable. Oops. Let's do something else too. Let's print out the length of our list. How many people have we found so far? So we'll print out a loop counter, and we'll print out how many names we found. And we'll do that on the big, and we'll do that on Hank's just to make sure things work. Hank's won't get to 1,000. We'll run it on Imdb Okay, that's kind of showing us some stuff, but you can see that it's starting to slow down. I'm going to add flush equals true on this just to make sure that things come out smoothly. You can see that this is kind of jittery. So we'll put that in. Okay, 17 seconds. We had a little bit of time on because we're doing some extra stuff. We're not doing a lot of extra stuff. And 3 to 14 is not a huge jump. It's a minor thing. So let's start again with IMDb data. And run this. And now everything's coming out a single line at a time, but things are starting to slow down. And the more iterations we go, the longer it's taking us to get to the next iteration. Because now we already have to find 23,000, we have to search through 24,000, 25,000 names to find out whether this particular name is in the list. So, essentially, this if statement isn't a single statement. This if statement is actually saying for n in name list, if n equals name yeah. So that's essentially this single statement, name not in name list. That's essentially what this single line is doing. And it's taken us a while. We've read 74,000 lines from a file of 260,000. And we're getting slower and slower and slower. All right, so